And then at the very end, after talking about the inverse trigonometric functions and their derivatives, we'll just quickly, I mean, we did this last class, but we'll just quickly go over the differentiation rules and see if there are any that we missed, and just sort of like look at all of them sort of at once. Okay. So first, let's talk a bit about just regular trigonometry. So everything that you know about trigonometry, or everything that you should know about trigonometry, is all sort of based around this unit circle. And that is just a circle centered at the origin with a radius of 1. So I'll draw that in. There's the x-axis, there's the y-axis. It's got a radius of 1, so it's going to hit all these points. Just pretend that's a circle. Okay, so that's the unit circle. And there are various angles that you can make starting at the origin and sort of terminating with this circle. For example, you can have the angle of 45 degrees. But of course, we're not going to call it 45 degrees. We're going to call it pi over 4 radians. And in terms of angles, the whole circle is 2 pi radians around. And you always start from the positive x-axis. So here is the angle 0. So this is if theta is, well, let me just use an equal sign. That's theta equals 0. And if the whole circle is 2 pi radians around, that means halfway around must be pi radians. A quarter of the way around must therefore be pi over 2. Three-quarters of the way around must be 3 times that, because it's 3/4 of the way around. So that's 3 pi over 2. And there are all these angles in between, like pi over 4, pi over 3, 2 pi over 3. Here are just some random ones. Here, for example, is 2 pi over 3. Right, and you can sort of tell because it looks like it's 2/3 of the way to a entire pi. So it's 2/3 pi, or 2 pi over 3. This here is 11 pi over 6. And you can tell that because it's almost a 2 pi, right? 2 pi would be 12 pi over 6, but it's missing a sixth of a pi. So it's 11 pi over 6. This angle is also, if you started here at the positive x-axis and went backwards, that you could also call it angle negative pi over 6. it's not really the same angle, but it ends up in the same place. All right, so if we take this, just okay. So that's the unit circle and how angles work. The whole circle is 2 pi, and all the angles are just little subdivisions of that. Now, in terms of trigonometric functions, the trigonometric functions, like sine, cosine, and tangent, are all just about reading like these points on the unit circle where an angle terminates, or where an angle intersects with the unit circle, I guess. And then just reading the x value and the y value of those points in rectangular coordinates. So for example, sine, let's say sine of, and let's just do pi over 4. Sine of pi over 4 is whatever this value is right here. Well, and you're not necessarily going to be able to read it off the y-axis because it's not a nice rational number, but it is square root of 2 over 2. And you can, there's a way to memorize these from the first quadrant, and then just be able to extend that knowledge out to the rest of the unit circle. Y value of the point on the unit circle associated with that angle. Right, so the sine is always the y value of the associated point. Similarly, cosine because this is a 45-degree angle, you might be able to surmise that the x value of that point is going to be the same as the y value of that point because it is a perfect 45-degree angle. And it is. It is also square root of 2 over 2. And let me just erase these points that we're not going to. Just clean up a bit. The cosine of that angle is also going to be square root of 2 over 2. And they're not always going to be the same, of course. It just is in this case because we have the angle pi over 4, which has the same sine and cosine. Not all angles do. So the cosine is always the x value of the point on the unit circle. Associated with the angle. And the tangent is not something that is just easily you can't just necessarily look at an angle and know its tangent. Fortunately, if you know the sine and the cosine, you can know the tangent. Because the tangent of an angle is simply the sine over the cosine. So the tangent of pi over 4 is the sine of pi over 4 over the cosine of pi over 4. And that's true for any angle. Like that is the definition of tangent. It is the ratio of the sine to the cosine. Or of the x to the y. Oh, sorry, the y to the x. Okay. So in this case, we know that the sine of pi over 4 is square root of 2 over 2. We know that the cosine is also square root of 2 over 2. Anything divided by itself is 1. So the tangent is 1. Although you could certainly go through the trouble of, whenever you're dividing fractions, you keep the top fraction the same, flip the bottom one, and change it to a multiplication instead. Instead of dividing by a fraction, multiply by its reciprocal. But either way, you get 1. Okay. And although we won't get into it nearly as much, the remaining 3 trigonometric functions are simply the reciprocals of these. Though that knowledge is useful for changing around expressions and stuff. Yeah. Okay, so secant. So the secant of an angle is 1 over the cosine. It's the reciprocal of cosine. Which also means that cosine is the reciprocal of sine. So what that means is that whenever you have a secant, that means you have a cosine on the bottom. And vice versa. If you have a cosine, that means you have a secant on the bottom. And you can, change this around as much as you want. The cosecant of an angle is 1 over the sine. And the cotangent is 1 over the tangent. So if you just wanted a quick way to think about these, the sine is the y, cosine is the x, and the tangent is y over x. And the last thing we'll do before really talking about inverse trigonometric functions is I'm just going to show you guys all the values of the common angles, of the points, of the common angles on that first quadrant. Okay, so this is just the first quadrant of the unit circle. Where you got the positive y's and the positive x's. Here's x, here's y, here's 1, here's 1, okay. It's really bad, okay. Good enough. Okay. So there are a couple of, there actually aren't that many commonly thought of angles. Okay, so of course there's that 45-degree angle. The angle pi over 4. or 45 degrees, but we're almost never going to really use the degree measures. Just cause. But that's the angle right there. There's also this sort of 30-degree angle, and that angle is pi over 6. It's just, if if this helps you imagine where it is better, it's about 30 degrees. And these are all measured from the positive x-axis. Alright, so this angle right here is pi over 3. Right, you can imagine if halfway around the circle, over there is a full pi, this is about, a third of the way there. Pi over 3, 2 pi over 3, 3 pi over 3, or just pi. So that's about 60 degrees. And technically, I guess there are also these angles right here. They're much easier to remember. The one that goes straight up, that's pi over 2. Or 90 degrees. And the one that goes nowhere, it's just where you start, that's an angle of 0. It's an angle of 0 radians and 0 degrees. Okay. Now the sines and the cosines associated with each of these points are just the x and the y's of these, these points that are on the unit circle. I guess I'll do that in green or something. Well, clearly this is the point 1, 0, right? You can see that it's 1 on the x-axis and that it's got no, 0 for its y value. This is 1, 0. And you guys know that ordered pairs go x, y. So 1 is the x, 0 is the y. So what that means is that the cosine of this angle is 1. The sine of this angle is 0. And the tangent of this angle would be 0 over 1, or just 0. And while I technically could write all that down, it would take up a lot of space, and you can get that information from the point being 1, 0 anyways. This point right here, associated with pi over 6, that is the point square root of 3 over 2, which is around 1.7 or so. Which is around 0.85 or something like that. But square root of 3 over 2, comma, 1/2. This angle pi over 4, as we've seen, creates the point square root of 2 over 2, square root of 2 over 2. With pi over 3, you might see a sort of symmetry almost, in some way, with the angle pi over 6. And that symmetry means that it's going to be the same values, just sort of flip-flopped, because instead of being over here, it's up here. So that point is just going to be 1/2 for the x and square root of 3 over 2 for the y. And this point pi over 2, the point associated with the angle pi over 2, that is just going to be 0, 1. Right, so there is a sort of xy symmetry with these points in each other. So the x values of all these points are the sines of the are the cosines of the angles, and the y values of these points are the sines of the angles. If you wanted the tangent, you would just take the y and put it over the x and sort of like simplify that complex fraction. And if you want to know what these values are for any other part of the unit circle, well, if you're in the second quadrant, you just take all these values and slap negatives on the x values of these points, because they'll be over on the left. If you wanted, the fourth quadrant, which is like right below this one, you would take all these values and just slap negative signs on the y values, because that's basically, this, but like flipped upside down. And if you wanted the third quadrant, which is like, completely on the opposite side, you would slap negative signs on both the x values and the y values of all these. I guess you would still have to like figure out what to call the angles if you were in the second, third, or fourth quadrant, but you can sort of reason that out well enough. Well, I guess there's no reason I couldn't just, do a quick little okay. So if this is pi over 4, then this is 2 pi over 4, except I'm not actually going to write it for a reason I'm going to talk about in like half a second. 2 pi over 4, that just simplifies to pi over 2, which we already know what that is, so I'm not actually going to write that down. But this angle would be then 3 pi over 4, right? Pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, or just pi, 5 pi over 4, 6 pi over 4, or 3 pi over 2, and 7 pi over 4. And then doing it once more would give you 8 pi over 4, which simplifies to 2 pi. Okay. If I do that again with some other angles, actually, I think I can get both of them in one. Or both of the things I was going to do in one go. Okay. Now, if this angle is pi over 6, going that same amount again would result in 2 pi over 6. But that simplifies to pi over 3. Going a third time would result in 3 pi over 6, which simplifies to pi over 2. Doing that again would be 4 pi over 6, but that simplifies to 2 pi over 3. And doing that again results in 5 pi over 6. Which makes sense because, of course, another 6 pi over 6 would give you, or another pi over 6 would give you 6 pi over 6, which simplifies to pi. Doing that again would give you 7 pi over 6. Another time would give you 8 pi over 6, but that simplifies to 4 pi over 3. Nine pi over 6 would simplify to 3 pi over 2. This is 10 pi over 6, although you'll hardly ever hear that because it simplifies to 5 pi over 3. And so this would be 11 pi over 6. Let me see if I can do these like different color. Yeah, so the ones in green are the ones you'll often, you'll mostly see them referred to by, multiples of pi over 3. Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Whereas the ones that are still in red are ones that you're primarily going to see referred to as multiples of pi over 6. Okay, but if you wanted to know any of the sines or cosines of these other angles, you would just take, whichever one seemed like it matches, and then just put a negative sign on it, flip it over to whatever side you need. So, that's a basic, trigonometry, the primer. And so we're going to talk about inverse trigonometric functions now. Okay. And you're not going to have to know much about the shape of the graphs or anything like that. Not too much, anyways. You're not going to be asked to graph, 3 sine of 2x plus 5 or anything. So even though we've been saying inverse trigonometric function this entire time, that's sort of just a name. None of the trigonometric functions, sine, cosine, tangent, or even cosecant, secant, and cotangent, none of them really have an inverse function. That's because they're not, what we call one-to-one. And all that means is that, to be one-to-one, every x value that it ever reaches has to be unique, and every y value that it reaches has to be unique. Just meaning that if you draw the graph of it, it has to pass both the vertical line test, of course it has to pass the vertical line test to be a function at all, but it also has to pass a horizontal line test. And these functions, these trigonometric functions being periodic, do not pass the horizontal line test. So the next best thing that you can do is, since you can't actually find an inverse function for these trigonometric functions, is to sort of cut them down. So for example, here's the sine function, right? Here's the graph of the sine function, or, a portion of the graph of the sine function. Right. If you tried to find an inverse of this, what you would end up making is this. Let's see. Okay. Wait. Positive x, positive y. Okay. Is this abomination, of a graph? Yeah, that's not a function. That's because the original trigonometric function is not one-to-one. So what you do instead is you're going to try to restrict the domain of the original. You're going to try to restrict the domain of the original so that you can, just take that away, so that when you flip it, when you make it the inverse, and you just look at that portion, that portion is a function. This portion of the original graph is one-to-one, and this portion of the inverse now works. So you're just gonna, that's how these inverse trigonometric functions work. They rely on you sort of restricting the domain of these functions until they are one-to-one. That's gonna work a similar way for cosine and tangent and all the rest of them. So the place that we had to restrict this to is from this trough to this crest of the sine function. This has an x value of negative pi over 2, and this has a value of pi over 2. So the domain's been restricted to negative pi over 2 to pi over 2. And when we invert it, when we find the inverse, basically all the x's and the y's get flipped so that, what was the domain of the original becomes the range of the inverse and vice versa. And as I'm sure you know, the sine function, the original sine function, goes from a low value of -1 to a high value of 1. So what that means is that the range of this is negative pi over 2 to pi over 2. And the domain is -1 to 1. And here are the domains and ranges of the inverse trigonometric functions. So what we just saw, right, is this is sine. So to invert it, that must be sine inverse or arcsine. And so if you look at the sort of entry for arcsine here, you see that its domain is -1 to 1, right? Because that's the range of the original sine function. And the range is now negative pi over 2 to pi over 2, because that is the reduced domain of the original sine function. So it's the range of the inverse. So there are going to be graphs of these to show, but I'll just draw them right here anyways. So this one's the one that we just saw. Right, and the domain went from -1. The domain of arcsine went from -1 to 1. And the range went from negative pi over 2 to pi over 2. And it did so in this sort of way, sort of sideways sine function. Right, if you sort of tilt your head and then just sort of let that continue, you can sort of see how it came from the sine function. Our cosine is also going to have the same domain, right? Because the cosine function also goes from -1 to 1. But the part that it's going to be restricted to, and I'm just going to draw a quick, you don't have to draw this, but this is what the cosine function looks like. It looks kind of like the sine function, except instead of passing through the origin, it is symmetrical about the y-axis. So it looks like that. And so, of course, we can't cut it down to the same domain. That wouldn't be one-to-one. What would be one-to-one is if you restricted yourself to the domain 0 to pi. So that's what we're going to do here, and that's what gets flipped around to make our cosine. So if that restricted domain of cosine is 0 to pi, that then becomes the range of arc cosine. So this is just, and I'll erase this in a second, but that's cosine. So arc cosine is going to have a range of 0 to pi. If I were to imagine taking that and flipping it around, at 0 has a, okay. Okay, so this is, say, arc sine. Okay, this is arc cosine. And this is going to be arc tangent. Okay. Now the original tangent, the graph of tangent, right, the trigonometric function tangent, looks like, what is it? It's odd. Okay. It looks like this. It just sort of has these asymptotes that it sort of snakes in between, and that just sort of like repeats forever, right? So it's periodic in that sense. That's tangent. So of course, you can't flip this around and wouldn't pass the, both line tests. So you're going to restrict yourself, just like with sine, to this middle little branch, I guess, of the tangent function. And that's what you're going to invert, or you're going to take the inverse of, to create arc tangent. So if we were to take that and just sort of flip that around, that definitely goes from negative pi to pi. Sorry, negative pi over 2 to pi over 2 for its, the domain of tangent. So that's going to be the range of our arc tangent. So negative pi over 2 to pi over 2. Right, so this is tangent. And the range of tangent, well, those asymptotes clearly signify that it goes up on that right-hand side forever, and that it goes down on the left-hand side forever. So that's a range for the original function of negative infinity to infinity, which means that's going to be the domain of our arc tangent. And so instead of these vertical asymptotes like for the original, we're actually going to have horizontal asymptotes at negative pi over 2 and pi over 2. And the way that's going to be shaped is kind of like this. Alright, so that's just like if you took that sort of middle branch and just sort of flipped it over. Also, I just wanted you guys to know that it's like if you have any questions at any point, you should ask them. Really, you should. I welcome them. Otherwise, I'm just talking for 2 hours, which is probably more than I talk in a week normally. And just the other ones, they don't really matter as much. Well, I guess one of them does. Okay. So the last one, and I know this is going kind of slow, so I'll just say what the last one looks like. Okay, arcsecant, which is 1 over cosine. Cosine 1. Yeah, okay. So normally secant looks like 1 over. Secant is 1 over cosine, so it's just the reciprocal of all the values that cosine has, which means that it should look like this, right? It sort of has this also. It also has this asymptotic behavior, but it's just a bunch of u's going up and down and up and down. Which, again, is periodic. So we're just going to take this. It's weird. It's the last part of this first little u and then the first part of the second little u. But that's what's going to get flipped upside down. So this is secant. This is the last actually important one. Really, I could have even skipped arc cosine. It's the cofunctions matter less for reasons. So really, what we should be interested in is sine, tangent, and secant. But if we take that and flip it around, that's going to look like what, 0 to pi, negative infinity to infinity. Okay. Right. Asymptotes here, and here. And if we took that and flipped it around, took that and flipped it around, it would look like, oh gosh, what am I doing? Don't need this. Okay. If we took that and flipped it around, what it would look like is, okay, at 1 it goes higher, okay, yeah. Stand a little bit, there we go. Yeah, there's an asymptote at pi over 2. And otherwise, other than that asymptote, it goes from 0 to pi. So here's just the graph of the rest. If you ever wanted them, these slides are all in the Unit 1 folder, by the way. So if you want this as a reference, you can go grab it there. Okay. So that's sort of like the basics of what these inverse trigonometric functions are. Now we're going to spend a little bit of time trying to evaluate these inverse trigonometric functions. And it really is easy as long as you remember your unit circle. If you can, if you can find like sines, tangent, sines, cosines, and tangents, and stuff like that, you can find the inverse sine and the inverse cotangent, or the inverse cosine and the inverse tangent. Okay, so typically with a trigonometric function, these are inverse trigonometric functions, but with trigonometric functions like the original, like regular ones, the idea is that inside of a trig function, so for example, sine, cosine, or tangent, what you put into the function is an angle, right? Like 360 degrees, or pi over 2, or 11 pi over 2, or 11 pi over 6, or whatever. And what it comes out to, like what it evaluates to, is some sort of ratio. Whether that's just x, just a plain x, that's technically a ratio of like x to 1. Or y, that's a ratio of y to 1, or when you're working with the tangent, that's the ratio of y and x. But in whatever trigonometric function you're using, what's going to come out is a ratio, and what you're going to put in is an angle. Now what that means is that for an inverse trigonometric function, what you're going to put in is a particular ratio. And what's going to come out, what it's going to evaluate to, is some sort of angle. And so with an inverse trigonometric function like that, you're really sort of asking the question, what angle gives me that, sine or cosine or tangent, depending on what the inverse trigonometric function is. In this example, we would be asking like what is the angle that gives me that value of sine that we get. And that angle, is the answer to the that expression. And in fact, let me do this in blue and this in green. Okay, and if we just word the question like that, technically there are many angles that could give you any particular value of sine or cosine or tangent. But we got to remember that those domains are restricted. Right, arcsine, the domain of it or the range. The domain and range of it are restricted, so that there's only a certain range of ratios that you can put in, and a certain range of angles that can come out, as y values. So if you have an arcsine, the only angles you're going to be able to say come out as a result of an arcsine. That's the only angles that you're going to be able to get out are the angles from negative pi over 2 to pi over 2. For arc cosine, the only angles you're going to be able to get out are from 0 to pi. For arctan, the only angles you're going to be able to get out of arctan are negative pi over 2 to pi over 2, and similarly for the other functions. So I'm just going to write little notes here. Okay. So I'm just going to write a little note here that for arcsine, the range is negative pi over 2 to pi over 2. For arc cosine, the range is 0 to pi over 2. Sorry, 0 to pi. For arctangent, the range is just like sine, negative pi over 2 to pi over 2. And we already did arcsine, so. Okay, so for A, we're essentially wanting to answer the question, what angle measure gives a sine of negative 1/2? And that angle has to be, within this range, negative pi over 2 to pi over 2. And we just sort of draw in a little unit circle here, just a quick little one. Sine is the y value, so we're looking for a y value of negative 1/2, which, if this is the unit circle and it has radius 1, that's around right here. So we're looking for an angle that gives that y value. If I draw those in, drawing all the angles that give y values like that, that ends up being, this isn't really to scale, so, but that ends up being these two angles, which, you might find that that's 11 pi over 6, and that is 7 pi over 6. The problem with both of these is that they're not in this range. Now this range, negative pi over 2 to pi over 2, assumes that you're on this side of the unit circle. Okay. And the reason 11 pi over 6 doesn't work, even though it appears to be here, is because you actually have to go around all the way to get to 11 pi over 6. However, if you start at the angle 0 and go down, go backwards, you'll find that the same angle is also called negative pi over 6. And that is within the range of the arcsine function. So the angle that gives this sine of negative 1/2 is negative pi over 6. And that's the only one within that range. So for b, the arc cosine of 0, right? So remember that what goes into an inverse trigonometric function is a ratio. So we're basically asking what angle gives a cosine of 0 within that range of angles. Okay. Now, the range being from 0 to pi means that we're restricted from the angle 0 to the angle pi. And we're looking for a cosine of 0? Well, that means we're looking for an x value of 0. Which means that we're looking basically here. And there's only one angle that does that. That is the angle pi over 2. That is the only angle within that range that has a cosine of 0. So the answer to that is pi over 2. For the arctan of square root of 3, that's going to be less apparent because it's, that square root of 3 means, because it's an arctan, that means that square root of 3 is a result of taking some y value and dividing it by some x value. So it's not immediately going to be apparent what it is. Gives a tangent of square root of 3. Yeah, so since it involves a square root of 3, you can probably take a pretty good guess that it's going to be one of those like pi over 3 or pi over 6 ones. It's not something that I can necessarily tell immediately, but let's remember to restrict ourselves to this range, negative pi over 2 to pi over 2. Okay. Since this is a tangent and it's the ratio of the y to the x, there's not like a huge, or there's not like really a place to draw a line on the graph. Let's just try pi over 3, for example. Let's see what the tangent of pi over 3 would be. Remembering that pi over 3 has an x value, with the point associated with it has an x value of 1/2 and a y value of square root of 3 over 2. Okay. So the tangent of pi over 3 would be the square root of 3 over 2, the y value, divided by 1/2. And that actually does come out to square root of 3. So the angle that we're looking for is pi over 3. If we had gone with pi over 6 instead, that would have the x's and the y's like backwards to how we got them from pi over 3, and we'd end up with like 1 over the square root of 3, which would not be a proper answer to what angle gives a tangent of square root of 3. As for this last one, arcsine of 0.3, 0.3 radians is not like a well-known or like well-defined angle on the unit circle, so you would just have to, and I hope this works this time. Okay, I guess not. Okay. Blah, blah, blah. Right, negative negative pi over 6, pi over 2, and pi over 3, and then, okay, cool. Yeah. So just a small note is that, again, that the trigonometric functions do not really have, perfect inverses. Like in the same way that, like multiplying by 3 and dividing by 3 after that, like always gives you the same number back. The same is not necessarily true of the trigonometric functions and the inverse trigonometric functions because they only operate on restricted domains. So, for example, if you started with the angle pi and you took the sine of it, right? Here's the angle pi. The sine of it is definitely 0. But then if you went ahead to take the arc sine of 0, you would actually not get back the angle pi. You would get the angle 0. Because arc sine operates on this sort of restricted domain where the only angles you can get out are from negative pi over 2 to pi over 2. Right? So you can't ever get pi out of arc sine. Yeah. So it's not just like, oh, there's an arc sine and a sine, they cancel out and it equals pi. It's not always the case. That's really all there is to say about that. Okay. So these are the cases where they do cancel out. And you don't necessarily have to write this down, but just be aware that it is a thing that happens. As long as you're in this value of angles, of ratios, and within this value of angles, then yes, they will cancel each other out. As long as you're dealing with signs that are in between -1 and 1, which I guess you always are, it's impossible not to. And as long as you're dealing with angles in between negative pi over 2 and pi over 2, then yes, arc sine and sine will cancel each other out. Similarly, as long as you're operating, in between the angles negative pi over 2 and pi over 2, again, tangent and arctangent will cancel each other out. And last, as long as, don't worry too much about this one, it's going to be impossible to try to put, an x value that's in between, -1 and 1 into an arcsecant. But more importantly, as long as your angle measures are in between 0 and pi over 2, or in between pi over 2 and pi, then in that case, secant and arcsecant will cancel each other out. And it works similarly for cosine, cotangent, cosecant. Although you'll definitely be hearing less about cosine, cotangent, cosecant, right? Because these are the three important ones. So just be aware that they'll only cancel each other out the way that you might expect, if you're restricted to a certain angles. Okay, so yeah, I think we're making good time, or okay time. So we'll solve an equation that has to do with inverse trigonometric functions, right? Because we were just evaluating them before. We'll actually solve an equation involving them now, and then we'll talk about their derivatives. Okay, so here's an equation. The arctan of 2 times some sort of value minus 3 gives pi over 4. So basically, this thing that I'm highlighting in purple, that is some sort of ratio. That's going to be some value of tangent that gives pi over 4 as its angle. Yeah, yeah. So pi over 4 is within negative pi over 2 to pi over 2. So what you can do, as long as you're careful to check that like the angle you're working with is in the range of the inverse trigonometric function, one thing you can do is you can sort of behave like this. You can just sort of say, okay, well, I'm going to take the tangent of both sides to cancel it out. I mean, and you don't have to think of it as like taking the tangent and then like canceling these out. Like if you know what this means and you can rewrite it into, you know, this, then feel free to do that as well. Okay, so 2x minus 3, the tangent of pi over 4. We can actually evaluate the tangent of pi over 4 right now. Here's the angle pi over 4. It's got a y, that point has a y value of square root of 2 over 2, and an x value of square root of 2 over 2. So yeah, its tangent is 1. Square root of 2 over 2 over square root of 2 over 2. So 1. So tangent of pi over 4 is 1. So this actually turns into a very simple equation. Just, why am I adding 4? Okay, add 3. Get 2x equals 4. Divide by 2. Get x equals 2. Now we're going to spend the last 30 minutes talking about the derivatives of these inverse trigonometric functions. And just remember that in order to be able to do this, we needed that angle, the range of arctan, or the restricted domain of the original tangent, whichever way you want to think about it, is negative pi over 2 pi over 2. So that means that this is okay. Let's see, let's say with this equation that starts off with an arctan, it would be impossible to have an equation like arctan of 2x minus 3 equals pi, for example. You just wouldn't see that because it would never happen. Yeah, I suppose if you did, then it would just be the answer would just be like x. There's no value of x that gives that. If like let me come up with a different problem real quick. Let's say instead, don't write this down. Don't write this down until I'm sure that it's going to make sense. Tangent of x equals. Let's see, negative. Right, but what if we started with. I don't know that you would necessarily get the wrong answer, but you would at least not get all the right answers. So for example, if you just saw like this equation right here, sine of pi equals sine of x, and you took the arc sine of both sides, thinking that that's going to give you your answer, you get pi equals x, right? Or x equals pi. But that's not going to be all of the solutions because technically, okay, so we have the answer pi equals x, but that's not all the solutions because in the problem as presented, there are actually multiple solutions. X can be pi, that's of course that's an answer, but x can also be 0 because pi and 0 have the same sign as each other. So while you might not, if you don't pay careful enough attention to the restricted domain of the trigonometric function when you're using the inverse trigonometric function, maybe you won't get a wrong answer, but you at least will not get all the right answers. Okay. And so, there are 6 inverse trigonometric functions. You're only going to really need to learn the derivatives of 3 of them. For a reason that's going to become immediately apparent. Okay. This is an unimportant but interesting detail. Sometimes you can have transcendental functions that have algebraic functions as their derivatives. You may not have thought about it before, but for example, the natural logarithm is a transcendental function because it's based around this transcendental number e, 2.71 whatever, and yet its derivative is simply 1 over x. Completely algebraic, not involving e at all. Just this weird little detail. And this is also true for the inverse trigonometric functions. They are trigonometric and transcendental, but their derivatives are algebraic. And here they are. Okay. Let me just zoom in on them. I'm sure at this point, y'all just think of derivatives as like, just another one to put on the list of derivatives, probably. But these are the three that you're going to want to know. Derivative of arcsine is u prime over the square root of 1 minus u prime. And so this is in terms of u, meaning that these formulas will work even when there is a function, a separate function inside of the arcsine. So like, even if you have like arcsine of 2x or arcsine of 3x to the fifth, you just take the derivative of that inside part, that's that u prime, and slap it on there. So it's got like the chain rule sort of like baked into it, already. Being in terms of u, much like those derivative rules on that one page, that is in the that course content folder that I sort of peeked at on Tuesday. On Tuesday. If you're just interested in, for whatever reason, if you're just interested in the derivatives of like arcsine of x and arctangent of x, it's the same, just with the 1 on top, because x prime is just 1, and an x down here. So that's just 1 over square root of 1 minus x squared. Right, so these just use u instead of x, and as a result, because u can be something else, they have a u prime multiplied onto them for the chain rule. Okay, so and the ones on the right, they matter less, particularly because you can just take the ones on the left, slap a negative sign on them, and you have them. Right, so the derivative of arc cosine is just the negative of the derivative of arcsine. If you ever needed derivative of arc cotangent is just the derivative of arctangent, but with an extra negative sign. Same with arc cosecant, it's just the derivative of arcsecant with an extra negative sign. Okay, now, it seems like, in my experience, it seems sort of like easy for students to get these confused. So just make sure to, like, I don't know, I guess like pay attention to what makes them different. So the arc sign is, I mean, not that you can't see it, like it's right there, but like the arc sign is marked by having a constant minus, well, for now let's just say a constant minus a variable squared. Arctan is marked by having them added together. So you might also see x squared plus 1 because addition is commutative, whereas subtraction is not. And arcsecant, that's marked by having the variable squared minus, 1. These two involve square roots, the arcsine and arcsecant. I'm basically just like writing down details about these things that you are looking at right now, but and this also has an absolute value of x, or sorry, an absolute value of u or whatever you're using on the outside of that square root on the bottom as well. So just, those are all the little details that make these different from each other. Oh, sorry, what's that? Uh-huh. It would be, but the derivative of x with respect to x is just 1. So when it's just arcsine of x, there's no need to incorporate the chain rule, but if it were arcsine of, like, x squared plus 10x, then yeah, you would need to incorporate the derivative of that x squared plus 10x, multiply it in at the end or at the top. But if it's just x, then there's no need. Yeah. Just realized that we didn't really take a 10-minute break in the middle of class, so I'll just, I don't know, try to finish this up. Just kind of really into it. Let's see, okay. Alright, so let's differentiate some of these. Okay, so none of these are simple, as simple as like arcsine of x or arctangent of x or whatever. But they're not that bad at all. As long as you can identify what your u is, what your inside function is, then it should be no trouble at all. Once you actually do memorize the formulas for these derivatives. So u is 2x, which means that u prime is 2. Okay, so arcsine, the derivative of arcsine of u with respect to x is 1 over, u prime, right, because of the chain rule, over the square root of 1 minus u squared. Yeah, okay. So if you know this, and you know what u and u prime are, well, you can just slap that u down there, the u prime up there, and you're done. Okay. So u prime is 2. That goes on top. Then you got fraction bar, square root, 1 minus 2x, because that's our u, squared. And I guess if you wanted, you could simplify this to being 1 minus 4x squared. Right? That's, 2x times 2x is 4x squared. Here, while we're working on that, I'll write down the other two. Derivative of arctan. It's just no square root, just a plain u prime. Just a 1 plus u squared on the bottom, or u squared plus 1, whichever way you want to write it. arctan is easily the least complicated of all of them. And arcsecant, that is u prime over the absolute value of u, just in its absolute value bar right next to the square root, and not 1 minus u squared, but u squared minus 1. Okay, so the arctan of 3x, if you identify your u and your u prime, well, your u is 3x, meaning that your u prime is 3. Then you just throw that u prime and u in here. Okay, well, u prime is 3 over 1 plus u squared, so 3x squared, which simplifies to 3 over 1 plus 9x squared. We have arcsine of the square root of x. It'll be good to memorize this fact, which hopefully you would after seeing it enough times, but if u is the square root of x, or in other words, x to the 1/2, that means that u prime follows the power rule, and you're going to take, u prime is the derivative of u, so you're going to take that power, put it to the front, so 1/2 x, and you're going to decrease the power by 1. Now, if you have a power of 1/2 and you decrease that by 1, it's going to become negative 1/2. And so that negative power means it's actually like on the bottom, and the fact that it's 1/2 means that it's a square root. So it's a square root of x on the bottom of a fraction. Along with that 1/2 being in front, that results in 1 over 2 square roots of x. If you're dealing with square roots of x a lot, you're going to see a lot of this. So it would just be, instead of having to do this, go through this every time, it'd be probably pretty helpful to remember that the square root of x, the derivative of the square root of x is 1 over 2 square roots of x. But that's what u prime is. So if we take these and put them into the arcsine derivative, u prime is 1 over 2 square roots of x. That goes on top. That's a whole fraction that goes on top. Over the square root, because this is a derivative of arcsine. 1 minus u squared. Now u is a square root of x, so now we can simplify that to be how about instead of having it at the top, we just sort of like put it at the front. So 1 over 2 square roots of x times 1 over square root of 1 minus, if you take the square root of x and you square it, you just get x. And I guess if you wanted, you could then multiply these two fractions together, get yourself 1 over 2, and since these are both under square roots, you can sort of like combine them, just multiply them underneath that square root, and you end up with x minus x squared. Kind of a mess, but that's how it is when you involve square roots as pure u, as your inside function. And last, have one of these where the inside function is e to the 2x. Now the derivative of an exponential is itself times, you know, the derivative of the inside if you got to account for the chain rule. So if u is e to the 2x, that means that u prime is also going to have e to the 2x. But because of that 2x in the exponent, you're going to have to multiply by the derivative of that 2x, which is 2. So it's just 2e to the 2x. So u prime, and so this, we're dealing with arcsecant here, so we're just going to take our u prime, put it up here, take our u's, take our u and put it here. So for u prime, we got 2e to the 2x, right? That goes on top. And we got the absolute value of u. Now u is e to the 2x. Times the square root of e to the 2x squared minus 1. Now, exponentials are actually always positive. I mean, you can't exponentiate something and get a negative number, so we don't actually, so in this particular situation, we don't actually need these square roots. Let me just... Exponentials are always positive. Right, you can't take e and put it to any power and make it negative. It's always going to be like positive. It may be very small, but it's going to be positive. So in this particular situation, we can get rid of the absolute value bars. Now e to the 2x squared, have a power to a power, you just multiply the powers together. So we have e to the 4x underneath here. Minus 1. And last, now that that is outside of the absolute value bars and it's just a plain e to the 2x, you can actually cancel it out with the e to the 2x that's on top. So you're just going to have 2 over the square root of e to the 4x minus 1. Okay, and let me just look at this real quick. Blah, blah, blah. Okay. I mean, we talked about these yesterday, so yeah. I mean, these are just all the ones we talked about yesterday, plus the 6 that you technically know now, even though you only really need to know 3 of these. So there's no need to go over that. All right, so you can leave whenever you want.